Hello students, good morning everybody. I am N. Janardhan Rao. We have discussed the crystal, that is orderly array of atoms in space, and space lattice. It is a 3D, three-dimensional network of imaginary lines connecting the atoms in a repetitive crystal structure in space, and also unit cell. It is the smallest unit having the full symmetry of a crystal types of space lattices. Most of the engineering metals crystallize either in cubic or hexagonal systems. Today we are going to discuss crystallization, grain formation, grain size, grain growth, effects of rate of cooling, and these three stages of cold worked parts under annealing temperature, that is stress relief, recrystallization and grain growth. Let's discuss about the crystallization. Now, what is crystallization? It is the process of growth of crystals during conversion of a metal from the liquid state to the solid state. It occurs in two stages. Those are formation of nuclei or crystal center, and the second one is crystal growth from crystal centers. Now, you see grain formation, how the grains are formed in the metallic structure. The crystals made up of several atoms. The individual crystals are called grains. The visible mass of a solid metal is the combination of the grains as the liquid metal solidifies on cooling. The grain formation takes place gradually. Now, when the temperature of the liquid metal is dropped below its freezing point, then the stable nuclei appear at various points in the liquid. These nuclei act as center for further solidification. As cooling continues, more atoms tend to freeze and they may attach themselves to the already existing nuclei. Each nucleus grows by the attraction of atoms from the liquid into its space lattice. Crystal growth continues in three dimensions, usually along the axis of the crystal. Then these nuclei or crystals grow in an orderly manner into different structures like dendritic, lamellar needle type, or circular, depending on the rate of cooling and presence of impurities in the metal. But in the majority of cases, branched tree like structure of crystal is formed. It is called dendritic structure as shown in the figure. Let us see the dendrite structure. Here the figure showing early stages in the growth. When pure metal solidifies, each crystal begins to grow independently, that is from nucleus or center of crystallization. Nucleus is simple unit in crystal lattice. Crystal develops with the addition of atoms according to the lattice pattern, and rapidly visible dendrite or a tree, you can see now tree. Why it is called dendrite? Dendron is a name of the Greek. It is a word of the Greek. The meaning of the dendron is it is tree. The grain structure is developed like a tree stems, and another stems are formed. These crystals are absorbing the smaller crystals and forming bigger crystals. Like that it is developing as a tree. The heat dissipation will be taken in all the directions in the towards the smaller crystals. Now you can see a real metallic picture of the iron carbon material. You can see this is the backbone of the dendrite growth. First it will form this backbone, then these slowly absorbed by cooling. When cooling continuously taken place, slowly these stems are absorbing the smaller crystals, and the entire liquid metal solidifies and you will have a growth. This type of growth is called dendritic growth. Now you can see grain size, how the grain size is developed. Let us know. Size of grains is regular as long as they grow freely in liquid state of metals. The size of grains is determined by the relation between the rate of growth and the rate of nucleation. That means if you rate of growth, if you want to increase rate of growth, you have to increase the rate of nucleation. That is depends upon the temperature variation in the liquid metal. Now let us know about the coarse grained material. What is coarse grained material? This coarse grained material developed due to the slow cooling. Now let us see. Slow cooling results in less number of nuclei formed. Then a coarse grain structure will be produced. Here see, there are number of nuclei are lesser here. So that's why the crystal size is bigger, therefore number of crystals are reduced. That's why this structure we can say coarse grained metallic structure. Now let us see fine grained material. In fine grained material, the number of nuclei is high. When cooling takes place, more number of crystals are formed. Let us see what is fine grained metal. If the number of nuclei formed is high, a fine grained material will be produced. Rapid cooling will result in a large number of nuclei formed and fine grained size will be produced. This material exhibit better toughness or resistance to shock. It is also increases yield strength, tensile strength, etc. There are mechanical properties are increased. This fine grained material will provide more advantageous mechanical properties, whereas coarse grained material is not that much advantageous to use in different applications. Now let us see what are the other factors that increase the rate of nucleation. So the other factors are presence of insoluble impurities like aluminum and titanium. See, in pure metal only one metal is occupied, but if the metal is mixed with the another metal, then we can say it is called as an alloy. So the presence of insoluble impurities, some metals which are insoluble and which give some other factor, that is it will changes the increase of the rate of nucleation. Now you say you can consider another factor, that is stirring the molten metal during the solidification, which tends to break the crystals before they have changed to grow large. See, as we discussed, coarse grain material is disadvantageous. If the grain size is increased, we are losing some of the advantages in mechanical properties. So to avoid that, we are making stirring effect in molten metal. By providing this stirring, we can reduce the size of the crystal. So you can promote the fine grain material, which is more advantageous than the coarse grain material. Now let us see effect of rate of cooling on grain size. Now what is the effect on cooling? A slow fall in temperature promotes the formation of a lesser number of nuclei and hence larger size of grains. On the other hand, rapid cooling produces larger number of nuclei resulting in fine grain size. As we have already discussed, slow cooling will help to form a lesser number of nuclei, therefore the size of the crystal is increases, whereas in rapid cooling it restricts the growing of the grain size, therefore it creates more number of crystals in smaller sizes, which provides fine grain size. Now let us see another effect of grain size on mechanical properties. In mechanical properties, let us discuss about the fine grained material. In fine grained material, the effects are, it exhibits better toughness or resistance to shock. This is an advantages. These are harder and stronger than coarse grained material. It has greater yield strength, better surface finish and fatigue strength. Now you can see coarse grained material. It is rough surface finish but less tough. It is better machinability than fine grained material. It is difficult to polish. It exhibits higher creep resistance at higher temperatures. It may have cracks during quenching. These metals are good heat and electrical conductivity. Now let us see what are the factors promoting grain size. To promote the grain size, these are the factors we can see. Increasing the amount of cold working favors nucleation, decreases the grain size. So by increasing the nucleation, we can increase the number of crystal formation, therefore which promote the fine grain size and decreases the size of the grain. Now see another factor, increasing holding time at any temperature above the recrystallization temperature, which favors grain growth and increases grain final size. Now see another factor, lower the temperature just above recrystallization, finer the final grain size. By lowering the temperature just above recrystallization, we can reduce the size of the grain size, so that we can finer the final grain size. So you can promote the finer grain material. Now let us see another points on promoting grain size. Slow heating will form few nuclei which favoring the grain growth and resulting in coarse grains. Now another factor, presence of insoluble impurities like aluminum, titanium will finer the final grain size. Now see another factor, faster rate of cooling results fine grain structure and slow rate of cooling results in coarse grain structure. These are the factors can promote the grain size. Now let us know about the phenomenon of recrystallization. See, after solidification, there are some strains and stress, local strains and local stresses are stuck between the crystals, which are disadvantages in applications. To promote the mechanical properties, you have to do recrystallization process. Now let us see what is the phenomenon of recrystallization. Whenever a metal is cold worked, there will be appreciable change in some mechanical properties like yield strength, ultimate strength, hardness, electrical resistance, etc. But the properties like ductility and plasticity will reduce. Now you see some more points on recrystallization, and it is also there will be considerable amount of stress concentration at cold worked spots. Now see another point, these residual stresses are to be relieved before the metal component is put in use. Therefore another point, this is therefore cold worked spots are subsequently annealed through 3 stages. Let us see what are the stages. Now these are the 3 stages. One is stress relief or recovery, and second stage is recrystallization, and third stage is grain growth. Now let us see the stress relief. What is stress relief? It is defined as the process of releasing the internal stresses on a metal at relatively low temperature which are below its recrystallization temperature. That recrystallization temperature is about 0.1 multiplied by Tm. Tm is nothing but it is a melting point. Stress relief hardly affects the structure and mechanical properties of the metal. It reduces internal stresses and increases tensile strength. It is an important method for releasing internal stresses in casting forging and welded equipment, etc. It is often referred to as a stress relieving treatment. Now, let us know about the recrystallization. This recrystallization, it is the process which occurs with heating in excess of that used for recovery. In this process, new grains are formed and thus the metal is set to recrystallize. Now, here the recrystallization temperature, it is about 0.3 into Tm for pure metal, whereas 0.5 into Tm will be the analloy, where Tm is the melting point, it is in Kelvin degree. Now, let us see another one, that is now important points on recrystallization. Due to recrystallization, the tensile strength and yield points are sharply reduced while the ductility is increased. And the next point is it improves the corrosion resistance. And next point is the greater the amount of cold work, the finer the resulting grain size. This is usually followed by grain growth, during which growth of the larger recrystallized grains occur at the expense of the smaller ones. Soluble impurities raise the recrystallization temperature. For example, pure aluminum crystallizes below room temperature, whereas commercial aluminum requires heating about 150 to 200 degrees centigrade. The recrystallization temperature largely depends on the degree of previous cold deformation and temperature at which the deformation is carried. Severe cold work will result in lower recrystallization temperature. As the temperature of the cold worked metal is raised, the rate of recrystallization increases. Recrystallization reduces tensile strength and yield strength and increases ductility, corrosion resistance. When the greater the amount of cold working, the finer the resulting grain size. Let us see some of the recrystallization temperatures of solids. Now, you see some of the temperatures of pure metal on recrystallization. You see the table, this is pure metal, these are the recrystallization temperature in degrees centigrade. For iron, the recrystallization temperature is 450 degrees centigrade. For copper, the recrystallization temperature is 200 degrees centigrade. For aluminum, 150 degrees centigrade. For nickel, 600 degrees centigrade. For low carbon steel, 560 degrees centigrade. For zinc is nearer to room temperature. Not only zinc, for lead also it is nearer to room temperature. At room temperature, the structure will be recrystallized, which grow the mechanical properties. Now, let us see the grain size after recrystallization. It depends upon the degree of prior deformation and it is holding time above recrystallization temperature. It is depends on annealing temperature, it is depends on heating time, it is also depends on insoluble impurities, it is also depends on rate of cooling. You can see the grain sizes here. This is a coarse grain size, as you all discussed. The coarse grain size is bigger, the crystal size is bigger than the fine grain material crystals. Here you see fine grain crystals, the crystal size is smaller than the coarse grain crystal size. Now, let us see grain growth. For further increase in temperature of the metal, the newly formed crystals continue to grow. Large grain size metals are highly ductile but of low strength and hardness. Therefore, coarse grains are not desirable in the final structure. Now, let us see cannibalizing of small crystals by larger ones. How this is cannibalizing? Here, these are, assume these are the crystals between the boundaries. You can see this is a curvature of the line between the crystals. You see the direction of the movement of crystal boundaries away from the crystals, but the crystals are towards the smaller crystals. These are the bigger crystals which are absorbing the smaller crystals, so that the entire crystallization taken place, it finally it becomes solidified and the dimensions will be reduces. Now you can see clearly here it is a bigger crystal. Bigger crystal is tends to grow, which is growing in all directions. You see direction of movement of crystal boundary. When it is growing in all directions, at the boundaries, if there is any small crystals, those crystals will be absorbed by the bigger crystal. In that way the crystal size is increases. This is the process of cannibalizing of small crystals by larger ones. Now let us see the diagram. This diagram showing that is annealing temperature versus mechanical properties. In this diagram there are three parts, that is already we discussed the stages of the phenomenon of recrystallization. First stage, you can see this is recovery and this is recrystallization, this is grain growth. In recovery the crystal sizes are slightly bigger, whereas in recrystallization the crystal sizes are smaller. But after recrystallization again the crystal size is increasing, which is disadvantageous in mechanical applications. You see in recovery the strength and hardness is high, whereas the strength and hardness slowly decreasing in recrystallization and also in grain growth, whereas internal stresses are high in the recovery, slowly this is decreasing in the recrystallization and grain growth. And ductility is in recovery it is low, but slowly it is increasing in recrystallization and also in grain growth. And now he see the grain growth will not taken place in the recovery, but as the grain growth first it is increased and slowly decreased, and again it will starting increasing, therefore the crystal size increases. Therefore after recrystallization if you increase the temperature, it is disadvantageous in many applications. So this is the mechanical properties versus annealing temperature. In this session we have discussed the crystal, that is orderly array of atoms in space, and space lattice. It is a 3-dimensional network of imaginary lines connecting the atoms in a repetitive crystal structure in space, and also unit cell. It is the smallest unit having the full symmetry of a crystal. Types of space lattices. Most of the engineering metals crystallize either in cubic or hexagonal systems. Crystallization, grain formation, grain size, grain growth, effects of rate of cooling, and these three stages of cold worked parts under annealing temperature, that is stress relief, recrystallization and grain growth. With this we are closing this session. Thank you.
Hello, good morning students. Today we are going to study one important chapter, that is types of cast iron. The cast iron is a very useful ferrous metal for domestic purposes as well as industrial purposes. It is produced in the cupola furnace by remelting the pig iron. As per the iron carbide diagram, more than 2% carbon is called as cast iron. The cast iron is having low melting point, so most of the cast iron components are produced by casting process. The cast iron is a brittle metal and having better vibrations damping properties. Now we are going to see what is the general composition of cast iron, what are its advantages and disadvantages of cast iron, and what are the various types of cast iron, what is the composition, properties and applications each of them. Let us see the advantages of cast iron. The cast iron is having following advantages. 1. It is having low melting point, that is 1140 degrees centigrade to 1200 degrees centigrade. Second, it possesses higher casting properties as high fluidity, low shrinkage, casting soundness, etc. They can be machined easily. And fourth, it having excellent vibration damping properties. Fifth, it possesses high compressive strength ranging from 340 to 930 Newton per mm square. Finally, the sixth advantage is it having good wearing and abrasion resistance. Now we will see what are the disadvantages of cast iron. The cast iron also having the following disadvantages. 1. It having poor weldability. Second, it is a brittle material. Third, it cannot be rolled into sheets. It is having low ductility than the steel. And finally, fifth disadvantage is it is very poor to corrosion resistance. Instead of iron, the cast iron is having the following general composition. It also having silicon 0.5 to 3.0 percentage, and it controls the forming of carbide in cast iron. And second composition, sulfur 0.06 to 0.12%. It affects excess sulfur content increases the possibility of cracking at elevated temperatures. The third constituent is phosphorus. It is from 0.1 to 0.3%. It reduces toughness and makes the cast iron brittle. Fourth constituent, manganese. It is generally from 0.12 to 1.0%. It controls the effect of sulfur in the cast iron.
Further clarification, contact the Additional Secretary, State Board of Technical Education and Training, 7th floor, BRKR Bhavan, Tank Bund Road, Hyderabad 500063. Fax 040 322 0546.